Well, class, I want to welcome you back to Episode 2 of Math 1050 College Algebra. I'm Dennis Allison here in the Math Department at Utah Valley State College. And today we're going to be talking about Cartesian formulas on the Cartesian plane and the equations of circles. But you know, before we get into this, let me remind you that there were 18 problems in the review pages on the website. You may have had a chance to look at that, I hope, by now. And remember, if you look on the web page for Episode 2, you'll find the answers for all those problems. And you'll actually see them worked out. So that's something you'll want to check out if you haven't done that yet. Also, from Episode 1, you may recall that I mentioned one of the important differences between college algebra and intermediate algebra is college algebra focuses much more on graphs. Not completely, but there's a lot more graphing in this course than you saw in the previous course. And in the previous course, it was more algebraic computation, factoring polynomials, solving equations, things like that. But now we turn to something new. Now, this course actually includes within it a lot of what you would call analytic geometry. Back in the 17th century, the XY coordinate system was first introduced, and that gave an opportunity to combine geometry and algebra. Prior to the 17th century, geometry and algebra were considered two separate branches of mathematics that had little or nothing in common. So, for example, if you would write an equation like this and showed it to someone prior to the 17th century, if you asked them what this is, they wouldn't say that's the equation of a straight line, because they wouldn't know anything about graphing. What they would say is this is an algebraic equation with two unknowns, and it has lots of solutions. For example, one solution is x equals 2 and y equals 2. Another solution is x equals 0 and y equals 4. Or another solution is x is equal to 5 and y is equal to -1. And that was as far as people got with that. Now, if you mention lines, people would think of lines as they were related to geometry. For example, in a high school geometry course, you study the relationships between lines and circles, that lines together can make triangles and polygons and so forth. But that lines were considered a strictly geometrical idea. Well, along comes this guy named René Descartes. As a matter of fact, we have a picture of him in the book we're using right now. He was born in 1596, and he died in 1650. He was French, and you know, back in those days, his name was probably spelled D-E-S, and then a separate word, C-A-R-T-E-S. So it was like two words, and since then it's been combined into one. Now, the idea that he had was that when he studied mathematics, he wanted to reduce things to the most simplistic form that he could. And he approached philosophy in the same way. You may have come across the same fellow in a philosophy course. In fact, I believe someone told me before class they're taking Intro to Philosophy. Was that in here? Yeah, Matt. What have you heard about this fellow in your philosophy course?
Well, that he wanted to test truth by doubting everything and starting with the most basic concept that cannot be doubted, which translated, he had said cogito ergo sum, I think therefore I am, which was the most basic truth, that he knew he existed because he thought. And he approached philosophy the same way he did with math, by taking the most basic concept and building upon it.
Right, exactly. You know, I think in the discipline of philosophy, I think René Descartes is considered the first modern philosopher. In mathematics, he's considered the first modern mathematician. And it's really for sort of the same reason that he tried to distill things down to these basics. In philosophy, he began with, what's the most basic thing I can know? For example, I exist. And he said, well, how do I even know that I exist? And his conclusion was that I think, therefore I am. That is, someone's asking this question about my existence. That must exist. So he proceeds from there to build his philosophy. And many later philosophers begin in the same way. Can we really trust our senses? Can we trust what we see and hear? Or can we be fooled? How many of you have seen the movie, The Matrix? Okay, so yeah, every one of you have. Well, you know, in that movie, let's see, who's the fellow? Is it River Phoenix? The stars in that? I don't know. I've forgotten who.
Lawrence Fishburne.
And Fishburne, yes. But you know, in that movie, the idea is that reality is not what it appears, and that he's in this so-called matrix, and he's being perceived. His entire life is not is not what it seems to be. Well, that's sort of right out of Cartesian philosophy, that whole idea. Okay, well, here's the notion that René Descartes came up with that's of interest to us. If you take a number line, a horizontal number line, call that the x-axis, call another number line the vertical y-axis, you can plot ordered pairs on here by going over, like, let's say if I go over 2 and up 3, if I go over 2 and up 3, then I locate a point, right up there, and we call that the point 2, 3. I think you're already familiar with this idea. Now, this is referred to as the rectangular coordinate system because, well, I can show you here, because when you move to that point, you move horizontally from 0, 0, the origin, and you go up, or you could go up 3, and then you could go over, but basically you're moving around a rectangle, so these are called rectangular coordinates. Also, if I call this the x-axis, and if I call this the y-axis, then this is called the xy coordinate system. But the last name for that coordinate system comes from his name. You see, this is René Descartes. I'm going to spell it separated like this. And this is sometimes referred to as the Cartesian plane. The Cartesian plane. So it's named after him there. The way he describes how he came up with this idea is he said that he was laying in bed one morning. He was accustomed to staying in bed late and sort of having a leisurely morning. He was laying in bed one morning. He was looking up at the ceiling, and there were these square tiles in the ceiling, and there was a fly that was landing in one place or another. And it occurred to him, for some reason, I don't know that it would have occurred to me, but it occurred to him, how could I tell somebody where the fly is? And he decided he could count so many spaces over and so many spaces up, and he could tell someone, an ordered pair, to tell them where the fly is located. And that was sort of the beginning of the idea that you could take ordered pairs of numbers and you could plot them, and you might get who knows what would hit C. So when he took a linear equation like x plus y equals 4, you remember we just looked at that a moment ago, when he plotted the ordered pairs, to his surprise, the ordered pairs lined up. They made a straight line. I mean, the average person might think that it'd just be sort of salt and peppered all over the place, that there'd be no pattern to where the ordered pairs were, but they actually made a geometrical shape. And with other equations, you can make the points become circles, you can make the points become parabolas, you can make them come to any other geometrical shape. And so that was sort of the beginning of this blend of geometry and algebra, and this is what we call analytic geometry. So I guess we could say René Descartes is the father of analytic geometry. And when we talk about graphing in this algebra course, we're basically doing analytic geometry. Okay, well, let's look at some formulas that are related to the Cartesian plane, and these formulas are referred to as Cartesian formulas. Now, the first formula deals with this situation. We have it on a graphic over here. Suppose I pick 2 points on the plane, and to make it general, I'll call this first point x1, y1, and I'll call the other point x2, y2. So x1 is the first coordinate, y1 is the second coordinate, etc. And the question is, how far apart are those 2 points? That is, what's the distance between them? Now, you see, the notion of distance is really a geometrical idea, because to measure distance, you'd think you'd need a yardstick or a ruler or a tape measure, something like that. And those are tools that come from geometry. But René Descartes found a way of measuring that distance using algebra to answer a geometrical question. Here's how he did it. If I pick the number down here on the x-axis directly below this ordered pair, I think that would be x1, because I go over x1 before I go up. And what number would this be on the y-axis? What would we call that?
Y1.
That'd be y1, of course. That'd be y1. And directly below the point x2, y2, this would be x2. And directly across from it on the y-axis would be y2. Now, here's the approach that he took. He said if he drew a horizontal line across here, and if he drew a vertical line across there and made a right triangle, he could figure out the length of the hypotenuse if he knew the length of the base and the length of the height by taking the base squared plus the height squared equals the hypotenuse squared. What theorem is that in geometry?
Pythagoras theorem.
Exactly. And you know, that's one of the few theorems that actually relates algebra and geometry prior to this period, because you have a right triangle and you have an algebraic equation, a squared plus b squared equals c squared. Well, so how long is the base? Well, the length of the base would be the distance between x1 and x2. And generally the way we find the distance between two numbers is we subtract them, x2 minus x1. But you know, in this particular case, x2 is bigger than x1, but in a different situation, x2 could be smaller than x1. So I'm going to put absolute values on there to make sure that I get a non-negative answer for that distance. And in the same manner, what would be the distance from y1 to y2?
y2 minus y1.
y2 minus y1, and once again, I'm going to put absolute values on there to make sure that that distance is never negative. Now, if I take the base squared plus the height squared, I get the distance squared. Let's see, so right here, this is the absolute value of x2 minus x1. Over here, this is the absolute value of y2 minus y1. And so let's work this out now on the green screen and see how that looks. I'm going to take the absolute value of x2 minus x1 squared plus the absolute value of y2 minus y1 squared, and that equals d squared. You see, this is actually an algebraic equation that's representing that geometrical problem. If I solve for d, then what I would do would be to take the square root of both sides, so I'll take the square root of this sum. But when I write this down, I'm going to drop off the absolute values and just say it's the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. Now, what makes that legal, by the way, for me to drop the absolute values all of a sudden?
You're squaring them.
Exactly, we're squaring them. You see, we didn't know if this difference was positive or negative, but in either case, the square will be the same. So there's no need to put the absolute values back in the problem at this point. And the formula that I have right here is referred to as the distance formula. I'll just put a box around that, and that'll compute the distance between 2 points. Now, here's the power of the formula. We have a little space here, so let's work a problem right here. I'm going to pick 2 points. Maybe you could pick points for me. I want a point P, and I want a point Q somewhere on the plane. Let's see, Matt, tell us just any ordered pair.
3, 2.
3, 2, okay. And Susan, what's another ordered pair?
1, 4.
1, 4, okay. Now, without even drawing an illustration, I want to find out how far apart these 2 points are. Now, you would think you'd need to actually see the points before you could say how far apart they are, but since we're not actually going to measure them with a tool, we're going to measure them algebraically, I can find the distance between those 2 points using this formula. Now, I need to decide which point's going to be x1, y1, which one's going to be x2, y2, and you can actually do this either way. Let's say we call this point number 1, and we'll call this point number 2. Then the distance will be the square root of, let's see, x2 minus x1. That's 1 minus 3 squared. And you'll notice, sure enough, that difference is negative this time. But when I square it, that won't be a problem. And then the other quantity is going to be 4 minus 2 squared. 4 minus 2 squared. So the distance between these points is the square root of negative 2 squared plus 2 squared. So the distance then is the square root of 4 plus 4, or the square root of 8. Now you remember last time we talked about simplifying radicals. Although technically this answer is correct, if I simplify it, how would I write that?
2 root 2.
2 times the square root of 2. Very good. 2 times the square root of 2. Now, if you take out your calculator, you could take the square root of 8, or you could take the square root of 2 and then double it, and you would see the same decimal appear. But you know, neither one of those decimal answers is actually accurate. Those are both approximations of the true distance. This is the true distance right here. Or I guess you could say this is the true distance if I hadn't reduced it. But if I took out a calculator and computed this, I would get a decimal answer that would terminate after 6, 8, 10 decimal places, depending on the calculator you use. And the reason for that is when you have a square root and a number under the square root that's not a perfect square, so you can't completely eliminate the square root, these are called irrational numbers. And the important characteristic, one of the important characteristics of irrational numbers is, in decimal form, they never terminate and they never repeat a fraction or never repeat a decimal. So I would leave the answer like this and not even use a calculator to approximate that. Okay, let's take another problem that pertains to these formulas. What if I plotted 2 points or 3 points on the coordinate plane? And let's see, I picked out 3 ahead of time for us to plot. Let's take the point 3, 2. 3, 2 is right here. There's the point 4, negative 1 right here. And the point negative 2, negative 3 right here. Now you notice those 3 points, if I connect them, make a triangle. And it looks like it's close to being a right triangle, but we don't know for sure. I can use the distance formula to figure out if this is a right triangle. Let's see, this is the point 3, 2. This is the point 4, negative 1. And this is the point negative 2, negative 3. What I could do would be to find the distance between these 2 points, the distance between these 2 points, and the distance between these 2. And I could check to see if the squares of the 2 shorter distances is equal to the square of the largest distance. And if it is, then by the converse of the Pythagorean theorem, then this is a right triangle. Let's just try this on the green board and see what happens. Okay, so we have a segment that goes from 3, 2 to the point 4, negative 1. And then we have another segment that goes from 4, negative 1 to the point negative 2, negative 3. And then from negative 2, negative 3, then we come back to the point 3, 2. So I want to check each one of those distances and see if they satisfy the Pythagorean theorem. I'll call this distance D1, D2, and D3. Distance D1, let's see, distance D1 is the square root of, let's see, I'll call this point number 2, 4 minus 3 squared. And then negative 1 minus 2 squared. And that is the square root of 1 squared plus negative 3 squared. So that'll be 1 plus 9 is the square root of 10. And I can't reduce the square root of 10. There aren't any squares in it. And I don't want to use a calculator because I want to keep the exact answer at this problem. Now I'll go to distance number 2. This will be the square root of negative 2 minus 4 squared plus negative 3 plus 1, because I have to subtract a negative 1. Negative 3 plus 1 squared. And that's going to be the square root of, let's see, negative 6 squared is 36. And negative 2 squared is 4. That will be the square root of 40. And I can reduce that. What would be the simplified version of the square root of 40?
2 square root of 10.
2 square roots of 10. And now the last distance, D3, is the square root of 3 minus negative 2. Let's just take a shortcut here. 3 minus negative 2 is 5 squared. And 2 minus negative 3 is 5 squared. So what we have there is the square root of 50, 25 and 25. Are there any squares that will divide 50? Yeah, 50.
25.
25 will, sure. So that's going to be 5 times the square root of 2. So here are the 3 distances. And now we have to decide which one of those is the biggest. Well, we have the square root of 50 is this one. We have the square root of 40 is this one. And the square root of 10. So it looks like the square root of 50 or 5 square roots of 2 is the biggest. So I'm going to be calling this distance C, and I'll call these others A and B. Let's go back to the green board. Okay, so from 3, 2 to 4, negative 1, we said that was the square root of 10. From 4, negative 1 to negative 3, negative 2, negative 3, we said that was 2 square roots of 10. And along the third side, which we are wondering if that's the hypotenuse, that's 5 square roots of 2. Okay, let's calculate or use the Pythagorean theorem to see if the equation's satisfied. I'll take the square root of 10 squared plus the 2 square roots of 10 squared. And the question is whether that will be the square root, no, 5 square roots of 2 squared. Let's see. Well, how much is this quantity? The square root of 10 squared is what?
10.
10, right. That's what the square root means, is if you square it, you get 10. And this one, well, if I square the 2, I get a 4. And if I square the square root of 10, I get a 10. So sure enough, that's 10 plus 40 is 50. And over on the other side, this is 25 times 2, and that's 50, because that was the square root of 50 to begin with. So sure enough, those are equal, and so this is a right triangle. Now, in what branch of mathematics, say back in high school, in what branch of mathematics would you have seen right triangles more than in any other branch?
Geometry.
In geometry, okay. So we found out that this is a right triangle in geometry, but I didn't use any facts from geometry. I used analytic geometry. I used algebra to solve a geometry problem. Now, in other cases, you can use geometry to solve an algebra problem. So that's the important aspect of the coordinate plane and analytic geometry, is that you allow these two branches to really become one, and they can play off against each other. Okay, let's go to a different problem that involves some new Cartesian formulas. And this problem is to find the midpoint. Okay, this time I have the same 2 points I had before, x1, y1, and x2, y2. But the question this time is to find the midpoint. Now, you know, in a high school geometry course, you do find the midpoint using a compass and straight edge. If you remember, what you do is you open up your compass, you put the needle here, and you make a big arc like that. And then you flip the compass over, you put the needle here, you make an arc coming back this way. Then you draw a line through there, and you find the midpoint. It's a technique from a geometry course. Well, I want to find the midpoint using algebra rather than geometry. So what I'm going to do is I'm going to come down to the x-axis x1 like we did before, and this is x2. And the midpoint should be halfway between these two. So the way you find, oh, that would be x bar. So the way you find a number halfway between two numbers is you add them together and divide by 2. You average them. For example, if you were a student in one of my classes and you came in and you said, Dennis, on the first exam I made an 80, and on the second exam I made a 90. Could you tell me what my average is? Well, the average is the number halfway in between, if there are 2 scores, so it'd be 85. And so the average here will be the midpoint between x1 and x2. And the way I'll calculate it is I'll average x1 and x2. Let's go to the next graphic and I'll show you what I mean. You see there's a formula for x bar shown on the left, and it's x1 plus x2 divided by 2. That's the middle number between x1 and x2. We'll do the same thing for the y's, and y bar is y1 plus y2 over 2. So those are the two midpoint formulas. Let's just take an example of how we would work that. Suppose we were given 2 points. Let's say we're given a point P whose coordinates are 2, 3, and I'm given a point Q whose coordinates are 8, negative 5, 8, negative 5. Now, I could plot those 2 points on a Cartesian plane, and I could connect them with a straight line segment, and I could use a compass and straight edge to locate the midpoint. But instead, without even plotting them, we'll be able to name the midpoint x bar, y bar. That's the question. What is the midpoint? So to calculate x bar, what I do is I average the original x's. That's going to be 2 plus 8 all over 2. 2 plus 8 over 2. And that's going to be 5. And y bar is going to be 3 plus, plus 3 plus negative 5 all over 2. And that's going to be negative 2 over 2 is negative 1. So the midpoint has coordinates 5, negative 1. 5, negative 1, right there. Okay, so that's what we're going to use the midpoint formulas again in a moment, but at least that gives you an example to see how I use it to calculate a point in the middle. Okay, now I want to look at the equation of a curve on the coordinate plane, a curve that you're familiar with, but it's not a function, it's the equation of a circle. Let's suppose that suppose that on the xy plane, I choose a point to be the center of my circle, and let's say this is the point HK. And I use that for the center, and around it, I draw a circle. I'll just kind of roughly sketch a circle right here. It doesn't necessarily go right through the origin, but it looks like I've drawn mine through the origin. And it looks like the radius here is r. Now, if I have a set of points that form a certain curve, I might wonder if there's an equation that all those points satisfy. And there is in this case. If I pick a random point on the curve, let's say I pick a point up here. For lack of a better name, I'll call it xy. I could have picked it here or here or here, anywhere else. But if it's on the circle, there's one thing for sure I know about it, and that is the distance from xy to the center is r, just as it was over here. Now that's going to allow me to find the equation of this circle. Let's go to the green screen and we'll see how that's done. I'll write that out. The distance from xy to hk is r, period. Now, this is a sentence in English, and I'm going to change it to a sentence in mathematics. For example, the word is translates as equals r. And the distance from xy to hk, well, now we have a distance formula for that. That would be x minus h squared plus y minus k squared. So the distance is equal to r. Now, you see what I have now is an algebraic sentence as opposed to an English sentence. And when you hear people say that mathematics is a language, this is exactly what they mean. I didn't translate that sentence into Spanish or German or French. I translated into mathematics. So maybe in some sense you should get a foreign language credit for this course because it is another language. This is the equation of the circle, except I want to reduce it. And what would you suggest I do to make that look a little simpler?
Square both sides.
Square both sides, okay. So I have x minus h squared plus y minus k squared equals, now I have to square on the right too, r squared. And this is the equation of the circle, but it's simpler than the one I had up above. As a matter of fact, this is referred to as the center radius equation of a circle. And I think we have a graphic that has this on it. Let's go to that graphic. Yeah, the center radius equation is x minus h squared plus y minus k squared is r squared. And we've just derived that formula. Let's work an example right below this on the screen. Suppose we had a circle whose center was at 3, negative 1. And let's say its radius was 5. We know the center, we know the radius, so that circle should be, as they say, well defined. There's only one such circle with this center and this radius. So what is its equation? Well, its equation would be x minus 3, because h is 3 here, plus y minus negative 1. What am I going to put here?
Y plus 1.
Y plus 1, right. Y plus 1 squared equals 25. That's the equation of the circle. Now, if I were to multiply that out, I could make the answer look different, but it's still equivalent to it. I just don't see the center, and I don't see the radius squared over there. If I multiply this out, this would be x squared minus 6x plus 9 plus y squared plus 2y plus 1 equals 25. Is that large enough for you to read? Can you read that okay? Okay, and if I rearrange terms, I have x squared plus y squared minus 6x plus 2y. Let's see, now I have a plus 10, and if I bring the 25 over, that'd be a minus 15 equals 0. If I write the equation in this form, this is called the general or the standard equation of a line. You notice I no longer see the center like I could see the center before. I no longer see the radius, so this has merely been expanded and in some sense simplified. Depends on your point of view what simplify really means. So now let me take another example that involves the center radius equation and the standard equation. I think we have another graphic coming up that has the general equation on it. Let's go to the second. Yeah, there it is. So as a general rule, would say that the general equation can be written in the form x squared plus y squared plus ax plus by plus c equals 0. A, b, and c are just some real number coefficients. What if I gave you this equation of a circle, x plus 4 squared plus y minus 6 squared equals 4. Who can tell me the center of that circle?
-4, 6.
-4, 6. Very good. -4, 6. It's not 4, -6 because h and k were subtracted. So -4 was subtracted here. 6 was subtracted.
You wrote it wrong.
Oh, I wrote it backwards, didn't I? Yeah, -4, +6. Yeah, I got it exactly backwards. -4, +6 is the center. And what is the radius?
2.
2, yes, because this is the square of the radius. Exactly. What if we take this circle, x squared plus y squared plus 2x minus 10y minus 3 equals 0. Now, what's the center and the radius of this equation? Well, of course, the problem is it's been expanded and changed, so we can no longer see the center and the radius. So I think if we could get it back in the form of the previous problem, we could read off the answer. To do that, I'm going to put all the x's together, and I'm going to put all the y's together. And the 3, I'll move out of the way. I'll bring over here to the other side. Now, I want to complete the square. What number should I add on here to complete that square? To make this a trinomial square. Do you remember how that goes?
You get the middle and you divide it by a half and then square it.
Yeah, you take the middle number and you multiply it by a half, or divide by 2, and you square that. Now, if I divide 2 by 2, I get 1, and when I square it, I get a 1. But if I add a 1 there, I need to add a 1 over here. I'm kind of running out of room, so I'll just put a +1 right below it there. Same thing here. If I take half of this coefficient, or if I divide it by 2, half of -10 is -5. If I square it, I get 25, and then I'll need to add 25 over here. Normally I'd write that out horizontally, but I'm kind of pressed for space. So this is now a perfect square. What is this the square of?
X plus 1.
X plus 1 squared, very good. And what's the other one squared? Let's see. Jeff, what's this other one squared?
Y minus 5 squared.
Y minus 5 squared, yes. And that's going to equal 29. Now can you tell me the center and the radius for this circle? Matt, what would you say?
Well, I'd say that the center is -1, 5,
-1, 5.
and the radius is 5.
Let's say
square root
29.
of 29.
Square root of 29, yes. So it turns out in this case, the radius is not a nice integer. It's the square root of 29. Without a calculator, could anyone tell us, like, between which two consecutive integers this lies between? Stephen?
5 and 6.
Between 5 and 6. Yeah, the square root of 25 is 5. The square root of 36 is 6. Would you guess this is closer to 5 or closer to 6?
Closer to 5.
Yeah, tell us why you think.
Well, because it'd be the square root of 25 is 5, and the square root of 36 is 6. It's closer to 25 than it is to 36.
29 is relatively closer to 25 than it is to 36. So if I were going to guess, I would say this square root's probably about 5.4, somewhere in that ballpark. You could use a calculator to check it, but we'll leave our answer like this because this is the exact answer. Now, if I plotted a circle, located the center at -1, 5, and if I made a radius a little bit over 5, maybe 5.4, 5.5, it'd be kind of hard to estimate that if you draw it, especially freehand. But if you draw that circle, you are drawing a graph of this equation right here. Let's take another circle problem. This time I'm going to draw a circle, and I want you to tell me what its equation is. So let's use a graphic that I've already made up. Here's an underlying sheet for it. Okay, I'm thinking of a circle, and the center is right here. And the circle looks like this. Okay. I want to find out what's the equation of that circle. Now, you can think of the equation of a circle as being like the name of a person. My name is Dennis. My name is Mr. Allison. You have names. People call you by different names at home and at school and so forth. But they all refer to you. And this circle has various names, but they're both equations. There's the there's the center radius equation, and there's the general equation. I think probably the center radius of the equation is the one we'd come up with. What's the center of this circle?
3, -3.
Looks like it's 3, -3. Yeah, 3, -3. And what's the radius of this circle?
3.
Looks like the radius is 3 because it looks like it comes up tangent right there, and also tangent right here. Those are both 3 units. So I bet the radius is 3 all the way around if it's a circle. So its equation would be what, Jeff?
X minus 3 squared plus y plus 3 squared equals 9.
Yeah, x minus 3 squared plus y plus 3 squared equals 3 squared or 9. So that's the name of this circle. If we wanted to take the time to multiply it out in combined terms and put everything on one side, that would be the general equation, but I don't think we need to do that right now. Okay, let's move on to another problem. What if I were given a function, and the function rule is 2 minus x. Now, if I were to graph that, what would it look like? Jeff, what were you going to say?
It'd be a line going through the y-axis at where y is equal to 2 and with the negative slope.
Yeah, it would have y-intercept 0, 2, and it would have slope -1. It may look a little foreign because I have these written out of order. I could turn it around and say negative x plus 2. So when we see this equation, we know it's a straight line graph, and we know exactly how to graph it. What if I change the equation to this? Suppose I say, I'll call this one g of x, and this is the square root of 9 minus x squared. Well, that's obviously not a linear function, but it looks like it's a function. We have a function rule. What would you say is the domain of this function? Well, let's see. Now, the number under the radical can't be negative. So if I come over here, I know that 9 minus x squared has to be 0 or larger. So I'm going to solve this inequality. This tells me that 9 is greater than or equal to x squared. And if x squared is smaller than 9, that means x is pinned between two numbers. What is it pinned between?
Negative.
3 and -3. Right, very good. You see, x's can be negative, but when you square them, we just have to make sure we get no more than 9. So it could go down to -3 or 3. So I know that the domain of this function is the closed interval -3 to 3. Now, I want to draw a graph of this function, but I've never graphed it before. Here's how I would do it. I would replace the g of x with a y. Those are actually sort of interchangeable, the y coordinate and the g of x value. And because I've not seen this before, I want to see if I can make it, convert it, transform it into a form that I would recognize. So I'm going to square both sides. Y squared is 9 minus x squared. And does anybody recognize that? I don't think we've seen that before. What are you thinking, Jeff?
Well, it looks like the basic, the equation for a circle if you move the x squared over to the other side of the equation.
Yeah, if I move the x squared to the other side, that is if I add an x squared to both sides, I get x squared plus y squared equals 9. Now that's beginning to look like the center radius equation of a circle. I might even write that as x minus 0 squared plus y minus 0 squared equals 9. This is a circle whose center is at the origin and whose radius is 3. But, you know, a circle is not a function because a circle doesn't pass the vertical line test. There are vertical lines that intersect the circle more than once. But, you know, if I go back to, if I go back to this form, or this form up here, You notice y can't be negative because it's the positive square root, that is the non-negative square root of 9 minus x squared. So what this tells me is it's the upper half of the circle. I think I can just sketch this right over here on the side. If I go out to 3 and if I go back to negative 3, that represents the domain. And if I draw a semicircle of radius 3, so that makes this 3 up here, that is the graph of the function g. I'll just put a g beside it. What would you guess would be the equation or the function rule for the lower half of the circle if I wanted that instead? Yeah, Stephen?
Put a negative in front of the radical?
Yeah, if I had taken the negative square root, I would have gotten the lower half of the circle. When I take the positive square root, I get the upper half of the circle. So even though a circle isn't a function, a semicircle can be a function. And I find out that this is just a semicircle. Very good. Okay, this time I want to demonstrate an example of an inequality. What if I draw a circle? Let's see, I think I have another graph I can use here. What if I draw this circle, but I'm going to shade in a region. Let's say I pick this point as the center. And I'm going to make this dotted right here. That's supposed to be a circle. So. And I'm going to shade in the interior. Now, when you have a region sketched, you can sometimes represent that using an inequality. And what I will do is I will write the equation of the circle as if that were a solid circle with no interior shaded. And then I'll decide whether I want the interior or the exterior by converting that into an inequality. Can anyone tell me the equation of the circle that goes around this? Let's see. Well, we need to know its center. What's the center?
3, 0.
1, 2, 3, 3, 0. Yeah, 3, 0. And the radius is? Looks like the radius is 2. So the equation of the circle, if I had drawn a circle, would be x minus 3 squared plus y minus 0 squared, I'll just put a y squared, equals 4. But you know, if you want the interior of a circle, then what you do is you make this x minus 3 squared plus y squared is less than 4. It's now an inequality. Because if you remember, when we first started talking about circles, this was the distance from xy to the center squared, and this was the radius squared. And this time, if I pick a point, like right here in the interior, let's say I call that point xy, because it's on the interior of the circle, this distance is less than 2. And so when I square both sides, this is the square of the distance, and this is the 2 squared. The distance squared is less than the 2 squared. What would I do if I wanted the points outside the circle, out here?
Greater than 4.
Yeah, it would make that greater than 4. And what would be the difference if I put an equal sign right there, less than or equal to 4? What would be the difference now?
It wouldn't be a dashed line, it would be solid.
It'd be a solid circle plus the interior, because this says now the distance can equal, well, the distance squared can equal 4, or be less than 4. So points on the circle and inside. But since we didn't have that, I'll leave that out. Okay, what if I turn this around? I'm going to give you an inequality, and I'm going to ask you to sketch a graph of it. So, or we'll sketch a graph of it together. So let me write an inequality up here, such as x plus 1 squared. Tell you what, I'm going to put a 4 in front of this one. 4 times x plus 1 squared plus 4 times y minus 2 squared is less than or equal to, let's say 1. What if I put a 1 there? Well, of course, these 4s sort of make it look different. First thing we might do is just get rid of the 4s. I'm going to divide out the 4s. So dividing by 4, I get a 1/4 over on the right-hand side. But this is beginning to look like an inequality that involves a circle. The center of the circle is what?
-1, 2.
-1, 2. Very good. And the radius, a little different from the other examples, the radius is what?
1/8.
Is 1/2. Yeah, you see, this is the square of the radius. So the square root of 1/4 is 1/2. Right. So when I go to graph it, I think I'll just draw this one freehand up here. When I go to graph it, I'll locate the point -1, 2. Okay, here's -1, 2 right here. And I'm going to go out 1/2 unit, which means this is a pretty small circle I'm going to draw, 1/2 unit. When I do this in the inequality, should I make it solid or dotted?
Dotted.
Solid, I think, because it says less than or equal to. So if I go out 1/2 unit, we'll say that's 1/2 unit right there. And I'm not quite done. What do I still have to do?
Shade the inside.
Have to shade the inside, sure. So I'll shade the inside. And so the center actually satisfies the inequality. Okay, and if that had been greater than or equal to 1/4, I would have shaded the outside of the circle. Okay, very good. Okay, now class, in summary, I think we have one more circle problem that is on the screen now that sort of summarizes some of the information that we've just looked at. We're given a circle. It's centered at the point 1, -6, and the radius is 4. And I have 3 questions here for us to answer. First of all, find its center radius equation. Then find its general equation. But then there's a part C. Why don't we come back to part C once we've established parts A and B? So let's just see. The center here is at 1, -6, and the radius is at 4. Part A wants us to find the center radius equation. Jeff, what would the center radius equation be in this case?
X minus 1 squared
Right.
plus y plus 6 squared
Y plus 6 squared
equals 16.
equals 16. That's the answer for part A. That's all it takes. Now for part B, it said find the general equation. You remember that's a little bit different form. Susan, how would I find the center, the general equation?
Just by multiplying it out.
Okay, what would be x minus 1 squared?
X squared minus 2x plus 1.
Minus 2x plus 1, okay. And y plus 6 squared, I'll do that one, is y squared plus 12y plus 36 equals 16. You remember when you square a binomial, you square the first term, you square the last term, but in the middle, a lot of times students forget the middle term. It's this product doubled. It's 6 times y doubled, or 12y. Now if I regroup the terms, I get x squared plus y squared minus 2x plus 12y. And let's say I need to accumulate some constants if I'm going to set it equal to 0. I've got a 1, a 36, and a 16 I have to subtract off. So what constant would go here?
21.
21, yeah, 21. So this is the answer for part B. This is the general equation, or the standard equation of the circle. Now let's go back to the graphic. There was one more question. Part C says, is the point -2, -3 inside, outside, or on the circle? Well, you know, if I substitute that point into either of these equations, if I get the two sides to be equal, that means the point is actually on the circle. But if I get an inequality, it's going to be either inside or outside. I think what I'll do is substitute that point into the center radius equation. So if we come back here, I'm going to erase this second answer so that I can use the first answer. Now the point we were given, I'll call it point P, is -2, -3. I'm going to plug in -2 for x, so I get -2 minus 1 squared. And I'll plug in -3 for y. That's going to be -3 plus 6 squared. Now the question is, do I get 16 or more or less? Well, this is -3 squared, or 9. This is 3 squared, or 9. What I get is 18. Now I claim that means the point is actually outside the circle, because you see what I've done is to calculate the square of the distance from point P to the center. This is the square because I didn't take the square root of that. And so the distance from point P to the center is actually the square root of 18, not 4. I got more than 16 when I squared it. So my conclusion is that point P is outside the circle. Now, I mention this because if you draw a rather accurate graph of the circle that we started with, center at 1, -6, radius 4, it's going to be rather difficult to tell if -2, -3 is on the circle or not if you draw it sort of freehand. It's kind of hard to tell because it's very close to the circle, but we've determined is that it's actually outside. Okay, one more problem. There's a graphic called David and the big guy. Okay, you're probably familiar with this story. In the Bible, David and Goliath meet, and David has a slingshot, and he throws a stone at Goliath. So I have David located at the origin. The circle going around the origin represents the path of the slingshot, and at the point 5, 1, the stone is released, and it continues along the tangent line, and it hits the big guy on the y-axis. And the question is, how far away is David from the big guy? Now, this actually doesn't require that we know the equation of a circle. Actually, this is more closely related to equations of lines. But there's a circle in the problem, so I decided just to stick it in here at the end of this because I think it's a good application of mathematics to solving a quote, real-world problem. So I'm going to draw that illustration right over here. I have a circle. I find the point 5, 1. 5, 1. The stone is released, and it's going to cross the y-axis right there, but we don't know what that point is. It's probably further up than what I've shown it, but I don't have a lot of room here. Well, what's the relationship between the path of the stone and the circle? Well, actually, I think I just mentioned that a moment ago. It's along a tangent line. Now, what's the relationship between the tangent line and the radius to the center? How are they related, Stephen?
They're perpendicular.
They're perpendicular. Very good. Exactly. So you know what? If I could find the slope of this radius to the point 5, 1, I could figure out the slope of the path of the stone. What is the slope of that radius right there?
1/5.
It's 1/5. Yeah, because it looks like if we go over 5 and up 1, the rise is 1, the run is 5, the slope is 1/5. Now, with that information, I can figure out the slope of the path of the stone. What would it be?
-5.
-5, yeah. Technically -5 over 1, but we could reduce it to be -5. Let's see. I think with that information, I can figure out what is the actual equation of the path of the stone. Let's see. What do I know? I know the slope of the line, and I know a point that it goes through. So what equation from the last episode do I want to use here? Which linear equation?
The point slope formula.
Very good. The point slope equation. And how did that go?
Y minus y1
Uh-huh.
equals m times x minus x1.
Very good. Where x1, y1 is a point on the line. Well, you know, we have a point on the line. The point is 5, 1. So this would be y minus 1 equals m times x minus 5. But we also know m, don't we? So let's plug that in. Y minus 1 equals -5 times x minus 5. Now you might say, well, Dennis, that's well and good, but how are we going to figure out where the big guy is up here just by knowing that? Anyone have an idea what we should do now? Stephen?
Convert it to the slope-intercept form.
And how would that help?
Because the constant that's being added, the b, is the y-intercept.
That's the y-intercept, and that's exactly where the big guy is. So let's solve for y. Y minus 1 equals -5x plus 25. So y is equal to -5x plus what?
26.
Plus 26. Plus 26. Well, once again, the slope is -5. We already knew that. But what's important now is that b is 26. Now that's what we were after. So what that tells me is he's at 26 on the y-axis. And so how far is David from the big guy?
26 feet.
He's 26 feet away. So the answer is 26 feet. Exactly. Well, you know, what this problem does is it doesn't really demonstrate properties of circles so much, except it does use some geometry. More importantly, what it demonstrates is characteristics of straight lines. And I use the property that the tangent to a circle is perpendicular to the radius. That's actually a theorem in high school geometry, which you may or may not remember. Stephen remembered because he told us that those would be perpendicular. But we also use the fact that two lines that are perpendicular have slopes that are negative reciprocals of one another. That was an idea from the previous episode. And we use the point-slope equation of a line, and we use the slope-intercept equation of a line. Let me ask you another question about this problem. How long is the rope on the slingshot? Here's David. He's whirling a stone around his head. How far out is the stone as it goes around David? Well, I think that would be the radius of the circle, wouldn't it? And we know a point on the circle. So how can I get the length of the radius from 5, 1 to 0, 0, where David is? Using a formula from this episode.
Distance formula.
Very good, the distance formula. Okay, so the distance, which is the radius, would be 5 minus 0 squared plus 1 minus 0 squared. And I think when you work that out, you get the square root of 26. So it's a little over 5 feet. Well, class, let's see. What we've talked about today were several Cartesian formulas. There's the distance formula. There are the two midpoint formulas, x bar, y bar. Then we talked about two equations for circles. There's the center radius equation, and there's the general equation of a circle. And then we looked at a number of problems related to that. When we come back next time, we'll talk about graphing on a graphing calculator. We'll talk about plotting points to graph curves, and we'll talk about some fundamental graphs. I'll see you then.